Well, we are going to move on here. We were talking about like L'Hopital's rule last time, right? And so um, we are going to see that periodically. So like we want to be able to still recognize that, manipulate it. Like it comes up in like some random places throughout kind of BC here for us. But where we're going today is actually back to something that you would have looked at in pre-calc, yes? Like you do spend a little time with sequences and series. So we're going to look at the two types here. Now, of these two, what's going to be most important to us, like going forward, is the geometric, okay? And so what we're going to do today is we're going to talk about sequences and series in general. We're going to look at summation notation. We're going to look at the formulas and derive all the formulas for arithmetic and geometric, and talk a little bit why geometric here is something important. So let's just start. That is not what it should be. Apparently I copied the one I scribbled on. So now you probably don't need to write any of this probably down. There's maybe a few specific things to notice about sequences and series. And so I'm just going to try to highlight a few of those here. So first, a sequence. And the sequence is just a list, okay? So if I'm talking about an arithmetic sequence, I'm literally just talking about a list of numbers. And it says in an explicit order. And that just means that there is a first number and a second number and a third number, that you cannot mix them up because that would change the order. So there is something unique about that. So like when we see a sequence, like we're going to use these braces, and I want you maybe to think about this as like the function. It's the definition. It's like what defines the sequence's pattern. And then notice it's just values that are separated by commas, okay? And we have the first number in the list, usually a sub 1, but it doesn't have to be. An alternate first number in the list that's really common is a sub 0. Like sometimes it does make sense to like, in some of these countings, to think about, oh, that's the 0th number, which is the first number. So we'll talk a little bit more about that and see some examples of that. So the nth term is a sub n. So even here how I'm saying that, like that's just the subscript, a sub n, okay? And we have a couple possibilities here. Like, so when you see this like dot, 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 like we're literally saying goes on forever, so that's infinite, okay? If we wouldn't have the dot, 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 and that means it stops at some last number, that would be finite, okay? So just maybe something general, and this would be maybe worth just as the summary. A sequence is an ordered list denoted as braces a sub n. Ordered, that's the idea. There's a first, a second, a third, and so forth. So if I give an example here, I could say I have a sequence defined where a sub n is, like what if I just said a sub n is 3 n minus 1, okay? And then if I would go to list those out, so if I think about, so what is the set of a sub n, okay? So literally we'll be like substitute in, so let's substitute in the first value. So if I want to know what a sub 1 is, n is 1, and this is why I'm saying think about it like a function. So 3 times 1 minus 1, so 2. What's a sub 2? 5, 3, 8, and so on. And that now is infinite, okay? Because I'm saying and so on, ... So when we look at them, actually, let me just, I don't know why that's all that way. Let me just make a new page. So when we're looking at this list, so a sub n, 3n minus 1, and we look at this pattern, like when we look at a sequence and we examine its pattern, it could have a pattern, it doesn't have to have a pattern, okay? So don't think that every sequence has to have a pattern, because I could make something up like this, and this is a fine sequence. And because if I say, what is a sub 3, we should all be looking at 12 because it's the third number in the list. So like that's all that's making it a sequence. A sequence doesn't have to have a pattern, but we definitely are interested in sequences that do have patterns. And so when you look at this, and if you think about this as a function, do you notice that our pattern here had to be a +3 pattern? Because it's just the slope of this. Do you see that? Like literally, if this is 1, then 2, then 3, then 4, and so on, don't you just keep multiplying by another or getting another 3? So things like this. So if a sequence, so this is really an arithmetic sequence then. So arithmetic sequences. So a sequence where the difference between a sub n and a sub n minus 1 is constant. Arithmetic sequence where the distance, or the difference, sorry, between a sub n and a sub n minus 1 is constant. We literally call that value d, which is the common difference. The common difference. Now, sometimes people don't like that language of calling it a difference, because literally in this one, the common difference is 3, and we tend to look at that as an adding pattern when we look at the list, right? Because the first value here, so thinking like just listing this out again, so 2, 5, 8. Like, but do you see like why it's maybe described that way? So if I take a number in the sequence and I subtract the previous number, doesn't that have to give me the amount going forward? It's just how it was described. It could have been described as an addition, like of saying a sub n minus 1, and thinking about what I'm adding to that to give a sub n, but it just wasn't, okay? So, if I asked here that I would like to find a sub 40, that's pretty easy. So if I'm looking for the 40th number in the list, like in fact, can you tell it to me? No work, answer? 119, right? I'm just going to literally put a 40 into that function, right? So if I have a function, that's great, because then it can define those values really quickly. What if I don't have a function, but I only have the sequence? So what if I'm given the following sequence? So let's say 4, 9, 14, 19, 24, okay? So a common thing here might be to go, okay, I am looking for a certain number in this list, okay? Maybe I'm looking for a sub 30. So notice that there's really a good benefit in knowing what a sub n is, because once I figure out what a sub n is, I put a 30 in for n and I get my answer, right? Now, first, arithmetic?
Yes.
Definitely. Okay. So now you could look at this. So what I maybe want to consider is, like, you could look at this and go, okay, plus 5 consistently, so it must be 5n. You okay with that? This number here should have been, or will be, this number here if I go backwards. Can you think as to why? Like, so I'm saying, like, if I go backwards, that should have been a -1. And so, like, that would be, like, the term that preceded this first value. And notice that when n is 1, I do get 4. When n is 2, I do get 9. So what makes sense to you about, like, this one that was before that I didn't write, but whatever the number would have been is this answer?
If 4 is a of 1, then then the number behind 4 would be a of 0, which if n equals 0, then it would just be the thing added to it.
Yes. And so could you tell me, like, graphically, what is -1 for, like, if we're thinking algebra 1, -1 is the y-intercept, and that matches when x equals 0. So again, there's another thought of, like, going backwards there kind of gives it to you. So that's great, like, if you have all of that. But I want to, like, maybe produce another statement here. And so you should be able to convince yourself this is true. So a sub n, so here if I want a sub 30, I can put a 30 in, life's good, right? Get our answer. So what if I wrote this, can you convince yourself that this is true? So a sub n is equal to a sub 1 plus d times n minus 1. A sub n is the first number. So be sure you separate the number versus what position it holds, right? When I write a sub 1, I'm really talking about 4 from that list. When I write n, I'm not talking about any of those numbers. I'm talking about what position they're in. That's the difference. So, like, when I say a sub 30, that's the 30th position. That's the n value, right? So why am I writing an n minus 1 times d? Talk about that at your table. What makes sense to you about why is it 1 less? It's related. All of this is related. Go ahead, go. Talk to each other. What do you think?
So 1 minus 1 could be 0. Change by 0 and just be like, yeah.
Because you're just trying to find position. So it's like if n is 30, we're doing 30 equals whatever is in 1 is 4 plus, and it'd be 5 times 29, or 5 times 2.
But it's only one spot over, so it's
Can somebody say it? Anybody know? What you got? After all that time? Okay.
We were talking about how because you start with the A1, that D is just telling you how many times you like count up by, in this case 5. And you have to take the minus 1 because you're starting at A1, whereas if you were to start at an A0 term, you can take the minus 1.
Correct. So when we think about, like, if I start at A1 and I'm trying to get to A2, I don't add twice, I actually add once, right? If I'm trying to get to A3, I would add twice, not 3 times. It's always 1 less because I'm starting somewhere, in this case, on 4. Like, sometimes I think about it as like you're like hopping on rocks, right? How many jumps do you have to take to get to 14? It's 2 jumps, and that's really what this is describing, okay? Okay, so arithmetic, sequence, okay? Sequence, just a list. We have that. So let's switch it here, and I know you've seen this before, so I don't feel like I need to, like, spend lots of time with it. But I think the geometric ones here tend to be a little bit harder, and so they're a little bit more involved. So we might spend a little more time on the geometric today. And like I said, they matter more for us, to us going forward. So geometric. Sequence. So just as an example, like we've actually seen some of these in here even. Like, so when I wrote this progression, like we were actually adding them up, but we had like this progression the other day. This was the rectangle, like thinking about divide in half, divide in half, divide in half, and the areas of each of those. We were adding them up to make that argument, but if I don't add them, it would be a sequence. So if I'd ask you, like, what is the first rectangle here, like it would have an area of 1, the second one would have an area of a half, the third one would have an area of a quarter. So notice that the pattern here is actually multiplying by r, which is going to be the common ratio. It's a lot like the arithmetic that there is this like division to really describe what we see looking ahead as multiplication. So I might say this, so it's a sequence. Where a sub n is found by multiplying a sub n minus 1 by a common ratio. And again, that's usually referred to as R. So I could say this, that R is some term divided by the term that came before it. So if you would take 1/2 and you divide it by the term that came before it, do you see that you're getting what we're describing as the common ratio of multiplying by a half going forward? Okay? All right? Still good? So I wonder if you could write an a sub n formula that is something like the geometric. There is also going to be an n minus 1 in it. So something like that starts with a1 somehow. So what could you put here that would describe that multiply pattern? Like it better have an r in it somewhere, and it probably needs an n minus 1 in it for a very similar reason that Tessa just described a second ago, right? So I'll give you 30 seconds. You know if you're right, because if you just make n equal 3, it better be 1/4 for this problem if you put all the values in. So a1 times, several of you said it, r to the power of n minus 1 is correct. Because if I'm trying to get to the third number in the list, how many times do we multiply by a half? Well, just twice, right? So like thinking about times a half, it's always one less because I'm starting at the first number. So this is the nth term of a geometric, okay? Now, honestly, like when we think about the sequence, we are in this course much less interested in sequences in general. We are much more interested in this series. We're much more interested in, can we find a sum of an infinite number of things, which I hope even makes sense when you think about the lesson today. Like we're summing up an infinite number of things. Like calculus is a lot about like an infinite number of things. So like, how do we like take this and extend it? So let's go ahead and do, let's talk a minute about a series. A series. And all I'm going to say is it's the sum of a sequence. It can really be, I think, just that simple to say. So, like we have already seen, that this is a series. And a series can be infinite or finite as well, right? So this one was an infinite series, and that we made an argument that based upon the rectangles here, that has to be a sum of 2, right? A series could be finite. So here's an example of one that would be finite. Just ends. Okay. It could be this. I didn't give myself enough room. We'll just cut it a little short. Can you spot the difference between these in terms of arithmetic and geometric? So I've already alluded to the top one's geometric, right? Because there's a multiply pattern. Second one, also geometric. The terms are generated by multiplying by 10. And the bottom one is definitely arithmetic, okay? I want to focus on the bottom one here and try to think about a formula that we could generate to find a sum of that list. Now, there is a story that's told about a mathematician and his tutor gave him this question. Like, so this was Gauss, like Frederick Gauss. You can look him up. You maybe have heard his name before. But so the story goes, his tutor gave him this task. He was maybe 5. Okay. I mean, he's probably a genius. Okay, but he does have a tutor at 5, so he's probably wealthy. But so anyway, so he came up with an answer in moments as a 5-year-old. Yeah, maybe. But I think we can be at least as clever as a 5-year-old, as a genius 5-year-old, right? Don't you think so? So let me tell you, like, I think that one reason. What if I just said it this way? It would be a really slow and bad idea to sum this up by saying, all right, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 15, 21, 28, and I just keep adding the next number. Is that even faster than you were going to do it? So, but it's going to start getting more difficult for me even to like, wait, what number was on? Because I got distracted for a minute. What number did I just say? So there's got to be a better way. So I want you to be at least as clever as a genius 5-year-old and come up with a better plan. Talk to each other. If you have an idea or seen something like this before.
So, yeah, but you take out the original.
Then you add one. Then you add one.
Or you do one plus one.
Because if you look at that, if you have to add
1 to 100. So every single time, two numbers should add up to equal to 100. 1 and 99. 2 is 98. 3 and 97.
No,
That's
but
like-
Like that, right? So then it should come to,
No, because you took it out.
because if we're doing 1 to 100, so everything is doing it except for 100. Because 1 and 99 are paired up, so 100 is by itself. So it'd be 100 plus,
no, yeah,
because it's 50.
Yeah, I don't believe this.
Oh.
It's highly likely.
I don't know, right? It is perhaps a little mythical about but if you look it up, this is a like told over the ages story. All right, let's hear some of your besting of the genius 5-year-old. Let's do it. There's more than one. There's more than one strategy here, and there's going to be one that I think we want to land on because it becomes the simplest, but I think it is less intuitive of the couple options. Henry, what are you thinking?
So I think you would do it by adding numbers on each end of the spectrum. So 100 to 1, 2 to 99, 3 to 98, 4 to 97, and those would each get 101. And you would be able to do that 50 times because you go towards the center, and then 50 times 101 is 5,050.
Yeah, that's basically what it said.
So let me see if I summarize, Henry. You said okay, take the first and the last, find that sum, which is 101, and then you keep grouping them in pairs. And so where'd the number 50 come from?
So it's just the total number of terms divided by 2 because you're combining two numbers.
Because we're taking them 2 at a time, so we definitely would have 50 pairs of 101. Okay? Now, Mahi, you were saying something slightly different, which is like it.
Yeah.
But, you're still grouping them together, but you decided to group these.
Yeah, and then just leave out 100 till the end and just add it up.
Yeah, the only thing you're going to have to consider if you do that method is do you notice that we have an odd number of numbers? Which means the number in the middle here of this list won't have a partner. So I'd have to count carefully or think carefully about that. What number is going to be in the middle of that list? 50, right? Thinking about the list when there's 100 numbers, the middle is not a value in the list. When it's odd, there will be a number in the list that will be the middle. And then so we'll have how many pairs, how many hundreds do we get? 49 plus this one, so there's 5,000, and then we get the 50 in the middle, 50-50, right? So a grouping strategy, though, I think is definitely key for a problem like this. I would say, I think Henry's involves less thinking about I don't have to consider the middle. I don't have to consider oh, I haven't added that 100 on the end. It kind of incorporates it as you go. So here's the formula for a finite arithmetic Is this a sequence or a series? Definitely series. Okay. So here's the formula. So it's going to be S for sum, the sum of the number of terms. So in this case, we're trying to, do you notice that n would be 100 here because we're saying add up 100 numbers? So look at the formula and see how this matches that description.
So it's basically like you're adding the first and the last terms, and then multiplying it by the number of terms divided by 2, so that turns them into pairs.
Correct. Yeah, and maybe we could just list what you just said. Like this will really say the number of pairs, and this would say the sum of each pair. Right? So in that example, we know the sum of each pair, the way that Henry did it, was 101. And how many of those do we have? Well, we'd have 50 of them because it's 100 divided by 2. Okay? Does the formula work if we had an odd number? So if I like throw away this 100 on the end and go, okay, I really wanted you to do 1 through 99. Like when I think about the number of pairs, like we've actually already decided what the middle number is in that list. What was it? What's that?
It's 50, but you get an extra half pair, so because of the n divided by 2 makes it 0.5.
Yes, so notice that the number here in the middle has to then be half of that sum, which then is going to be the extra half pair that we're talking about. So it doesn't matter if it's even or odd. Okay. Some of you are looking like you're not sure what I just said about the extra half pair. Take 30 seconds to table. Are you okay with that? Like why it's still going to work if it's odd, whether we include the 100 or not, and it's because of that 50 that's in the middle. We are never going to talk, ever, about an infinite arithmetic series, except right now. Because it's going to diverge. So this is never going to come up again because we're never going to say find the sum of an infinite arithmetic. And so when I'm saying diverge, so this is also language, I think I mentioned it like one of the first days. Like really what we're saying is that the sum like goes to infinity. It's just going to keep growing. So even if the common difference is 0.00001, if I kept adding that infinitely, right? If I just kept doing that forever, do you notice that my number could get as big as I want it to get? Right? It just will take a very long time by taking each step at once. It'd be very, very slow growth, but it could go as big as I want it to. So it's going to diverge. Now, when we think about geometrics, some geometrics may converge and some would diverge. So we want to separate that. So I'm just pointing that out. So let's go ahead and switch now, and let's talk about a geometric series. So let's go back to something like, how about something like this? 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus, we'll stop at 64 for now. Like powers of 2 are a little interesting maybe to look at because they kind of maybe give a clue as to some pattern here. Like when I'm thinking about adding these up, do you notice like, what if I back up? Okay, so my first value is 1. My next value is 2. It's this value that's been doubled, right? But my total from there is now 3, right? If I stop right here, my total is 3. When I add the next value in, my total is now 7. The next value happens to be 8, and then I add that in, and I get 15. The next value happens to be 16, I add that in. Do you see what's happening? Like you literally could could get the next number not by multiplying by 2, by thinking about what the sum is up to that moment, and then like, you know, adding 1, right? Isn't that what's happening? So I'm only saying that because there has to be a formula then that would somehow link this together the way it did for arithmetic, okay? So I'm going to write something here I think different for this one to help us maybe see it. So what if I say this? A sub n is equal to a sub 1. Now normally, I'm sorry, that should say s sub n. It's my fault. S sub n, sum. S sub n is a sub 1, and normally we would say plus a sub 2, right? Isn't that what I'm saying here? A sub 1 plus a sub 2. But I could just as well say plus a sub 1 times r to the first. Isn't that how I find it? That next number I would multiply by whatever r is. So I could say plus a sub 3, or I could say a sub 1 times r squared, right? Isn't that really a sub 3? Okay, so this pattern continues. And it continues. And then at some moment, I would write down r to the n minus 1. Notice that that would be a sub n minus 1. It's the next to the last term is really how you'd interpret that. I'm sorry, that is the last term. Sorry, that's a sub n. That is the last term. Notice that's the formula that we wrote down just a minute ago, right? So I should have probably written the next to last term as well, but whatever, it's fine. What would it be? You tell me. A sub 1 times r to the n minus 2. I'm just going back one more, okay? So, are you okay with what I've done here? I'm just writing it another way because I'm wanting to take advantage of in all of these, like isn't 16 just a bunch of multiples of 2 to get there, right? So I'm trying to take advantage of that somehow. So here's what we're going to do. If I wanted to, I could definitely multiply both sides of that equation by r. Why would I do that? I don't know, but I could, right? Agree? Yeah, I could. So let's do that. And when I do that, I would get an a sub 1 times an r. That's this one times r. Then this one would be r squared. And this one would be r cubed. And then this one would be r to the 4th, and that pattern continues. And so maybe I should have put it there because now I'm regretting that. So we'll put what Mahi said, an n minus 2 here. So that one would be an r to the n minus 1. And then my last one now is r to the n. Still with me? You might go like, I don't know what you're doing, or I don't know why you're doing it, but I understand what you did, okay? So here's the observation. Do you remember when we were like proving, like using Pascal's triangle, like some of those things first semester, and we realized all the stuff in the middle is going to kind of match up and kind of drop out, right? Do you remember that? This is kind of like that too, because when I think about equations or system of equations, can't I add or subtract true things and get another true thing? So what if I subtract, I think it'd be easier to subtract, it'll look nicer if we would take this one minus this one. Well, we can do either one. We just need to subtract them. We'll just have a negative in the wrong spot. I won't rewrite it, so let's just subtract it the way it is. Okay, left side. Well, that's s sub n minus r times s sub n. Right? That's all we have. It's just subtraction. But I'm saying, when I think about the subtraction here, do you notice these are dropping out? That doesn't, right? So that's stuck. What else do I have left? Okay, what sign do I put between them? Minus like this? And you said a sub 1 r to the n? And why is that subtraction?
Because on the a of 1 times r to the power of n is on the one that's subtracting.
Yeah, so it's just remembering that that piece is dropping out here, okay? Aiden, I'll get the rest of this posted, because this one's missing, I think, right now. Okay, that's nice, because notice that everything in the dot, dot, dot is now gone, right? So, S sub n, we could factor that out. And so if I factor that out, I would have a 1 minus r. And over here, we could factor out an a sub 1. And I get a 1 minus r to the n. So if I want to know what the sum is, it has to be that. Just dividing both sides by 1 minus r. So this is the sum of a finite geometric if we want to check it, like if I zoom out here a little bit and we just go back to like my made up times 2 example here. Okay, so if I highlight those 4 numbers in orange, like even the fact that I just said, well, you can't read that hardly now. Like that's n equals 4. You okay with that? 4 numbers, that's what 4 is. It's the number of numbers I'm adding. And a sub 1 is 1. And notice that's the only other piece we needed, right? Once, well, we knew r, because r here is 2, right? So if we just substitute that all in, so literally we'd say, okay, so a sub 1 is 1 times, so s sub 4 would be 1 minus 2 to the 4th over 1 minus 2. Confirm it worked. Like, we can see the answer. It should be 15, right? Is it? Can you do it in your head? I don't know what's happening.
Sounds like someone was like a
Could be dance.
Oh, they do dance.
There's that big room. Like, what's that? Like, anyway.
They're causing an earthquake. Why can't they do
Yeah,
that?
shaking. Yeah, the lights are
Did we get the right answer? Did we get the 15? Did you get it? Okay. So it works. All right, so we're going to extend it now super fast to an infinite one. So here's one that this is the one that we've already talked about several times, that we already are, like I made a geometric argument that this answer is 2, right? So here, r is equal to a half, right? And if I asked you what n was, well, really, it's a limit as n is approaching infinity, right? That's really what's happening for this one. Like, we wouldn't say n equals infinity. That feels a little awkward. But let's look back at like this formula again. So S sub n, a1 1 minus r to the n over 1 minus r. So if I want to do the limit as n approaches infinity of this calculation, and if r equals 1/2, what's happening here? If n is going to infinity and r is 1/2, what is happening to r to the n? It's becoming what? So it's approaching 0, which means the formula turns into this. So the sum of the infinite geometric is a1 over 1 minus r. Now if you try that for that question, like, so r1 plus a half plus etc. So for us, okay, a1, 1 minus r, 1 over a half, which is 2.
Can we go back to S sub 4? How did that come out? Because I might have done it.
This would be 1 minus 16, which is negative 15 over negative 1.
I got positive.
Yeah, that should be the sum of the first. It's the sum of the first 4.
Okay, sorry.
Yeah. So 12 plus 2 plus 1. Yep. Why did I want to highlight this? Do you have any idea? Because, like, here's a geometric. So 1 plus 2 plus 4 plus 8 plus 16 plus dot dot dot. So if I would, definitely a geometric times 2, so the infinite sum is a1 over 1 minus r, which is 2. What? The sum of that list has now somehow wrapped around the number line and we've come back around to the number negative 1? Look back at the blue and tell me why I should have never done that.
Is that really worse if r is less than 1?
Why? Tell me what's going on.
Because if it's above 1, then if n is, I mean, if r is more than 1, then n will make it go towards infinity instead of towards 0.
Yeah, so r to the n is going to grow, right? So 1 minus something going to infinity is, well, not 1. So, and that's what you're saying. So what about, so it is true that r has to be less than 1, but I want to be a little careful about saying that because the number negative 10 is also less than 1.
Bigger than negative.
It also has to be bigger than negative 1. Well, if it's 0, what does that say about your sequence?
0 is the infinity, which is not real. Oh, infinity is the same number. Because wouldn't r to the n be 0 to the infinity, which is just
Except, like, think about the list. You don't need the formula to write it. So here's my first number is 3. R is 0. What's the second number?
0.
What's the next number?
0.
What's the sum of that? Forever, if I'd add it all up. Okay, so like you could do it. So here's what we should say, that an infinite geometric will converge. It will converge if that's true. Notice it also shouldn't be, like, so thinking about the endpoints here, like we have a problem with it actually equaling 1 as well. Because notice if it equaled 1, you'd have something like this. If my first number is 2, my second number would also be 2. my third number would also be 2, right? If r is 1, I'm just going to keep writing the same number again and again and again and again. And that sum is definitely infinite as well. So it's going to diverge. It doesn't produce a sum, or the sum is infinite, unless r is between -1 and 1. So you can have, like, definitely have written this formula here down, but we definitely want to link it with that condition, okay? So it's only true if it converges. When you use it when it doesn't converge, it gives you really strange answers that really don't make any sense. Though you can find plenty of YouTube videos where people are like arguing about this like -5/12 as being the answer to the sum. It was like a physics professor at a college. I think he's making a joke, but then people started taking it seriously and it just became a thing. Like, anyway. So geometric, like even this idea, this is a pre-calc idea, right? Like you saw geometrics last year, should have. There are probably a half dozen questions on the BC exam that are multiple choice that you have to recognize that what you're looking at is a geometric sequence or series. And so it is really going to be really important to us. So where I want to go next here is we do need to talk about some notational things. And so one notation that we have to be really comfortable with is this sigma notation, which, you know, I barely mentioned it in class the other day because we don't really need it in AB when I put that sigma there. But if I wrote something like this, from n equals 1 to, let's say, 100, and I put n here. So first, like some language, like this is referred to as the index. This is the upper limit. So sigma is telling you to add, it's a sum. And think about this as like the function. It's really how you're defining the nth term. So like you could also think about this as like a sub n equals n, like that's really what that's describing. And so if you look at this answer, we've actually already done this problem, haven't we? Because this is saying, if you remember your sigma notation, it tells you to substitute in 1, get that answer, plus, now that is like an index, almost like in computer programming, if you write like a loop, right? So you're going to increase it by 1 and then do it again. So you're going to increase that by 1, plug it in again. Okay, so I just get the number 2. And I keep doing that until I reach the end of the loop, right? There's the condition to stop when n is 100. So that's the last value that goes in. And we already did this and proved we were more clever than a 5-year-old genius. Or at least equally clever.
What happens if the maximum isn't divisible by that n value?
Like for...
Like for the sigmas, like if you did like n equals 3 or something, and the maximum is like 101.
Yeah, so that's definitely possible. So let's illustrate that. So over here, if I would say what is a sub 1, I hope all of you would say 1. Okay, right? It's the first number that we're adding. So let's look at how this could change if I would write something like this. So n equals 3. Other things that we use for the index, like I is a common index, k is a common index. Okay, so just be okay with. Did you you just throw something across the room? Ashley, you want something like that?
Yeah.
So, and let's say I put in here again. So this, so if I ask you, what is a sub 1? It's going to be whatever that first value that gets substituted in. So this first value of 3, that is now a sub 1. So it's the first number in the list that we're adding. It's not the number obtained by substituting in 1. Okay? So a sub 1 is the first number we are adding. Not necessarily when the index equals 1. So here, like, notice that, like, if I would just start writing some of this out and think about the last number, do you notice that even though the answer isn't 50-50, like, we would still have a constant sum here and we'd have number of pairs. So if you wanted this answer now, you could say, okay, I know it's first number plus the last number. That's the sum, and then I need to multiply that by the number of pairs. So I would just need to be able to count that carefully. So from 3 to 97, how many numbers is that? Is it 94? Is it 95? Well, 3 is the first number. So how many numbers would 3 to 97 be? Answer? Votes for 95? And it's 95 because if you just say from 1 to 10, how many numbers is that? Well, it's 10. Boy, what's 10 minus 1? It's 9 because it's 9 beyond the value of 1, right? You're not counting that first number if you just do the subtraction. So we would just say then, okay, so it's 97 minus 3 is 94 plus 1, 95. So there's 95 pairs. Do the, divide by 2, sorry. I don't know why I did that. Let me try that again. So how many pairs are there? 95 divided by 2. So that is one way that we could see a summation. Like, so we could write out what it is until we make sense of it and then use another formula to get the answer. So did I answer that? Okay, so what about this? What if I would say the summation from I equals 2 to infinity of 3 times 2/5 to the I. Now, one option here is to tell me it diverges, so the answer is infinite, or you tell me a number. So maybe if you're like, I'm not sure, like maybe think about, notice here, like I didn't start it at 1 or 0, right? I started at 2. Why? I don't know, I just did. Okay. So you just have to take that into account. So what's the sum? I'll give you 60 seconds. 90 seconds. It's a long day.
Maybe improved.
There's gotta be a
Well, yeah, but it's approaching, like it's getting smaller and smaller.
They were gonna add those all added.
You're adding those
Yeah.
numbers together. You're adding these numbers.
So this case, R is
closer and closer to 3 every time.
I just put it in this thing. The
Oh,
A1.
yeah, that is fine.
Wait. This
So
is-
that's, and I'm
that's
seeing a
for
lot.
infinite, so is it?
It might be 3
Okay, but.
Yeah, it's,
So.
That's like that.
I was.
but the A is the.
I agree.
Okay.
It's either 3 or 3.
Yeah.
Because eventually you'll start,
Okay.
It's
you'll
just
start
in-
multiplying by small and then keep on adding small.
That's very good though, because I need to know everything.
Wait, you should use it in A1. To find A1. You use.
But you're multiplying, not adding.
I thought I was A1.
Like,
You could plug it in.
it's 3 times that value that you're just describing.
That's your function, it tells you what it is.
So then you're adding those values.
That's true.
Which is what?
Hold on, wait 2 seconds.
Yeah.
Oh, 4 between 5 times 3. So 12.
Cause you're saying the 2 over 5, the power of I is.
Or just 13 1.5.
Or you're saying it's.
Ought to be exactly half.
This answer, you ready? That was longer. That was longer than I said. Do you have a number? So 1.5. Anybody else?
1.
1. Anything else?
0.8.
So 4/5.
Yeah.
Okay. Anything else? Sadly, it is not infinity.
Is it 5?
Is it 3?
Let's go with that.
The sum is 5.
How do you do that?
Is it because it's like that S of infinity where it's A1 over 1 minus
Definitely
R?
is.
If
I did.
A1 is 3 and R is 2 over 5, so it would be 3 divided by 1 minus 2/5, which is 3 over 3/5, which is 3 times 5 divided by 3, so 15 divided by 3 is 5.
Why did I think R was in front?
Right.
That's
Right.
so slowly.
Do you do your math?
Yeah.
Did we suffer from algebra mistakes or conceptual mistakes?
Conceptual.
Conceptual, okay.
Forgot they did the whole thing.
What are you doing then?
Yeah, I don't know. That's somewhere not conceptual or or algebra. Like if you would like some of you were looking at this 2/5, and that's not a bad thing to look at, and the 2/5 itself does approach 0, right? But so here is a conversation we're going to have, and as we go forward, it's pretty easy with geometric to see that that these values individually are getting closer and closer to 0. Do you agree with that? Like the number I end up adding, as I would keep doing this, if I'd write out a list of 500 of these numbers, by the 500th number in this list, like it's getting small. Because it's going to be 2 to the 500th power, which kind of feels big until you turn around and divide it by 5 to the 500th power, right? So that fraction is getting smaller and smaller, then times 3, that fraction is getting closer and closer to 0, okay? So I'm going to make a statement. I want to be really careful because there could be a misconception that you generate right now. If a series has a sum, the individual terms must get closer to 0. But that's not guaranteeing there is a sum. Okay? So if I have a summation of a sub n, I will say, so I said this, if there is a sum, the limit as n approaches infinity of a sub n should equal 0. However, this does not guarantee a sum. Now, for geometric, it does work. Like for geometric, there's no problem. We actually just made an argument that that piece will force us to go to that sum. But there's going to be things that we're going to look at in the future, and it's worth like mentioning one of those right now as we look at and have you kind of explore it a little bit, even just as we investigate the summations notation here, okay? So here is a super famous series, because remember, that's really the goal for today. Not necessarily, not because we're going to keep seeing these. So here's a series. 1 over 1 plus 1 over 2 plus 1/3 plus 1/4 plus 1/5. And if that goes on forever, this answer is actually infinity. And a lot of times, like, this feels upsetting, and it doesn't feel like as matching what was just said. Because notice, individually, those fractions get closer to 0, don't they? If it's 1 divided by a bigger number, the fraction is getting closer to 0. But here's what that means. And who's in computer science? Any of you? Okay. I have something that Mr. Culbertson wrote that I can show all of you at one point. But here's what it means. If you would add enough of these, I should be able to say that this answer, so if I stop somewhere, I should be able to get a number, like, so like that side would be bigger than 100. Now, how many is that going to take? A lot. But it's possible. But the difference is, like when we think about, like when I wrote this could never do that. Like this, the most this could ever be is the value of 2. This one is somehow allowed to kind of escape. Like here, the sum converges down, right? Thinking about that geometric like argument, that's a pretty, like it will never escape the box. Somehow this sum does, okay? This is something called the harmonic series. It's literally like if you think about music and you take a length and you cut it in half and you cut it in third and you cut it in quarters, like that's why it's actually named that, okay? I'm going to maybe just say this. It is kind of the boundary point between things that converge and things that don't. So this doesn't converge, but just like barely. Like it is as close to the boundary of the things that converge as it can be. And there's much more we have to say about that, but that's not really the focus today, but it's going to keep coming up. But I just didn't want you to like start thinking, oh, yeah, if things get smaller, they converge. Like this one violates that, and I'll be able to show you more about that as to why. But let's do a few other things here. Okay. So if I gave you one like this, now, so here's maybe at this point, like these are going to get worse as we move away from things that are strictly geometric. Because what's going to happen in the future is we're going to have a series that is like kind of geometric. Okay? It kind of has a lot of the characteristics, but it violates it. And so we want to be able to recognize the geometric tendency and take advantage of it when we can. So my first observation here is notice that there's an exponent. And if this is the index, doesn't that mean the exponent is going to keep growing by 1? Do you see the geometric? As you look at this, if I asked you what's r, can you do it without writing anything out? R is the common ratio. What is the thing that I'm multiplying by as I keep going down the list? Somebody said it. Yep, it's a half, right? Because if n goes up by 1, don't you multiply by another half? So if we think about this, if this is geometric, well, what's a1? Now a1, again, is the first number that comes out, not necessarily when I substitute in 1, but notice that that agrees here. So what's a sub 1? 1. So what's this sum? What's this infinite sum? 1 over, which is? Which is 2. Notice this is the 1 plus a half plus a quarter. Do you spot it? Like if I substitute it in, it is it. But for when I start writing it differently, then you're like, that seems different. But I mean, this is like the 4th time that I've referenced this same series today, right? Like, so it's just getting used to like the notational changes for it. So again, if this would have said n equals 2, then nothing here would change except what, or this 1/2 wouldn't change, that wasn't supposed to be erased, but a1 would. So a1 would now be, it would be 1/2. So this would be 1/2. So the final answer is 1, which makes sense because we're really cutting that number off the list, right? So if the sum was 2 and you cut the first number off, now the sum is 1. Okay. Can start looking worse though. Now, this isn't arithmetic, right? So don't even think anything arithmetic. And even if it was arithmetic, I see an infinite there, I'm done. It diverges. I can't do it. It's not possible. This is geometric. And sometimes when you see questions like this, like it's really necessary for you to be good with your algebra and your exponents and to think of it a different way. So what I mean by that is if I would say, 4 times 4 times 4, this is 4 cubed, right? And if I would multiply by another 4 squared, wouldn't I add the exponents together? And that would be 5 4s, right? So when I'm looking at this exponent here of n plus 1, notice that that would be -3 to the first times -3 to the n, wouldn't it be? Because if the base is the same, I'd add the exponents, and wouldn't that give me an n plus 1? Now by writing it that way, it should help me think about how to combine that together to make sense of this. So this is an infinite geometric. Work together. What's the sum? You could, if you get stuck on a question like this, you could try to start listing them out, like writing the first number, then the second, then the third, adding them up, and just be able to see the pattern. Like, that's fine, but they get messier and messier. But I would say that's the second strategy if you don't spot it. So that's the fallback plan. Just write a few out and see if you can spot what the R is and what the A sub 1 is.
find them, how do your ends not cancel out? Go to the -3 end on top and 5 end on the bottom.
You would never do that if I wrote this. Because that's kind of what you're saying. Like, it doesn't, like when you see it with a number, like, because this is 9/25, right? That's the answer. It doesn't even simplify, right? But like sometimes when you see the n, you want to like really do something with it, but it would be just like crossing the 2's out here, and that's what I mean. Like you would never do that there, so don't do it with the n. If it was multiplied, Tessa, if it was multiplied, then you'd be fine to think about it that way. But just thinking about like the addition here really just means that you had that base times one more of them. So like if I would say x to the 2 plus 1, doesn't that mean x squared times x?
Yeah.
So like I'm just thinking about pulling that back apart as I'm writing this, and that's why you can't really simplify that exponent at all. Okay, look up here. Are you okay with, I did 2 steps here. Do you spot them? You okay with the 2 steps? Sudi's okay with the 2 steps? Rest of you? Tessa's okay? Paige is okay? So notice that there's a moment here that you're going to end up with a -3 to the n and a 5 to the n. And again, just properties of exponents, you can put it back together, which means right now you know what r is. -3/5. Okay, what's a1? It's 9/5. So the sum, the infinite sum here should be a1 over 1 minus r minus 3/5. That's really plus 3/5. That's 8/5 times 5/8. So the final answer is 9/8. Did I do my arithmetic right? He agrees. Okay. I want to do it another way because I want you to notice something. So looking at this summation from n equals 1 to infinity, and I want to go to this step for just a minute. So this moment from that summation, I claim it's equal to this. I claim I can move that out in front. So, am I right? If I'm right, you should be able to say why. If I'm wrong, you should tell me why I shouldn't do it. So, does it give the same answer? If it does give the same answer, then we better be careful or better be really clear as to why it's wrong. So, and if it does give the same answer and you're like, okay, that seems weird, it gave the same answer, then there should be a reason you could say. So take a minute at your tables, like, same answer? Is this 9/8 on the right? If I do the same work that we did before, like do the summation and then multiply it by -3, do I get the right answer? And if I do, why can I take the -3 out in front?
that makes
factor that
A
negative
of
3
1
out, put it on the outside.
I sum up everything.
Yeah, then
Everything by negative 3.
It's not the same.
So I think this is
negative 3 over A, and negative 3 over A times negative 4 is not A. So it's-
I think it works.
Negative 3 is not.
you can, it's not that it doesn't matter, you can just like, you can move it outside of this.
I think it works because like, it works for anyone. But isn't that just same thing.
It's not the same thing, but it kind of works for a very similar reason. So if you remember why I said that, like,
You can literally just take all of the 3s out, like if you like were to
Yeah,
write it out, you
because
can
it's
just take
just
all
you
the 3s
factor it
out,
out.
multiply them out at the end.
It's basically visually instead of multiplying them all as a whole.
Oh, yeah.
Like it's still multiplying them all by
yes.
3s, just after multiplying
Yes.
them by each other.
You mean adding them to each other?
After adding
Yes.
them to each other.
Yeah, so literally what's happening here, like if you think about the steps, so you're like, I think every table now is like realize, oh, they're the same, and it has something to do with like factoring it out, or it's in every group. So like if you substitute a 1 into this, think about what you'd be writing, negative 3 times negative 3 over 5 to the first plus. And then you're going to substitute a 2 in, and you're going to write a negative 3 times a negative 3 over 5 to the second plus. And every time I'm going to write a negative 3 times something. And over here, it's saying negative 3 times, now you do the sum. Substitute in 1, plus substitute in 2, plus, do you see it would just distribute out to be the same thing that you had on both sides. So maybe just an observation that you can factor out a constant from the summation. So like if we wanted to write that as a property, so if I had a summation from n equals 1 to, it doesn't matter, and I write a constant times x to the n, something like that. So, and we should maybe comment that b here is an element of the real numbers. We could bring that out in front. Something like that. If b is an x or something with a variable in it or with an n in it, definitely don't do that. I would really change everything because you'd be changing it as you went if you were adding. Okay? Is that geometric? Does it have a geometric pattern? If it does, you should be able to say what R is. So that's my first question. And then we'll finish with this one. What's R? Like, do you see, I just keep making it worse for you, right? I like add these like n's and then plus ones, and now I put an x somewhere, but don't do any different.
Factor out the x, so you can
Just be careful though, because this would really mean x plus 2 times another x plus 2 times another x plus 2, and all those x's would be multiplying. So you'd have to do like Pascal's triangle to rewrite it, and that feels messy.
yeah.
But that would be true, but I don't know if that helps us get R. So here's my hint. Like, just a minute ago, we decided R was negative 3/5, right? Because we saw we could rewrite this as minus 3/5 to the n. Because when n goes up, we multiply by another negative 3/5. So what is R?
Oh, it's x plus 2 over 2.
Is x plus 2 over 2. Right? Because you could rewrite this as x plus 2 over 2 to the n, just using properties of exponents. Now, so this is a real AP question, multiple choice, that they have, or at least a style that they have asked all the time. It says, what is the interval, which of the following is the interval of convergence for the series? And literally what they're asking is, can you figure out on what x is? What should x be that would allow this to give a sum? Now, if we know this is geometric, r should be between 1 and -1. So what should x be between? Okay. Because we're going to multiply by 2, subtract 2.
If it's 0, it's 2 over 2, which is 1. If it's -4, it's -2 over 2, which is -1.
Correct. That's another good thought. Did you notice what he just described? If x is 0, and you go back to this original problem, do you notice that becomes 2 to the n over 2 to the n? What is 2 to the n over 2 to the n? 1. So what does this series become? 1 plus, what's the next number? Still 1 plus 1 plus forever. Oh, that's infinite. Okay. If x happens to be the number -4, do you notice that -1, -1, -1, -1, -1, -1, and so we're divergent on the ends, doesn't have a sum. So this question right here, that's an AP question every year in the multiple choice. And that's why I'm saying that even today, this topic that's from pre-calc comes back and you're like, the key thought here is, do you notice that this could feel really intimidating until you recognize you need to rewrite it? Okay? So, I'm going to stop here. This is 8.1 in the math lab. It's what I've been calling 9.1, but it's 8.1 in the math lab. Okay? See ya.